Okay, welcome back. This is part 3 of our lecture about hypothesis testing. Man, hypothesis testing is brilliant. This is like one of the foundations of modern society. It's how you get new medicines, new innovations, new discoveries are made, etc. It's how social sciences work and natural sciences work. It's how the economy works in terms of like how businesses make decisions and so on. And you would think, man, this is a rock solid thing, and it is. The problem is, errors still happen. These hypothesis tests can produce the wrong result, and you have certain risks that different kinds of errors are going to happen. And that's what we're going to be focusing on today. How does, in this part of the lecture, how do we manage the risk of different kinds of errors so that these hypothesis tests do not lead us astray? I mean, so far we have developed a pair of hypotheses. In our silly little example, we've been talking about the relative heights of Creighton students and UNO students, but it could have been any number of things. And then we were able to compute based on samples of Creighton students and UNO students, we took the difference between the two averages and with a little math created a Z statistic, a difference between two means statistic. The Z statistic, if the null hypothesis is true, it is distributed according to a bell curve, and there's certain probabilities of getting different values along that bell curve. And based on that probability, you either choose to reject the null hypothesis, or you choose to not reject the null hypothesis. But how do you know if you've made the right answer? I mean, there's lots of ways this can have gone wrong. For example, when we computed Z, we found it was someplace along the horizontal axis. If it was near the hump of the distribution here, we didn't worry. I mean, it's clearly very typical according to the null hypothesis, but when it's out there in the tail, we don't. Now, if it's far enough along the tail, we get to reject the null hypothesis, but here's the deal. There is no far enough out into the tail. No matter how far out to the right on the tail of that distribution you're going, there is still a finite probability values that big of Z happen just by chance. Okay? Just by dumb chance, you can get a pretty big difference between two averages. Maybe you measured the Creighton basketball team when you took your 10 samples, and maybe, I don't know, does UNO have maybe a jockeys team where they race horses and they're those little guys, you know, whatever? Well, you might have gotten a huge difference between the two averages. But that doesn't mean there's actually a difference between Creighton students' height and UNO students' height. You just had a crappy average that wasn't very representative of what the real students look like. There's a finite chance that's going to happen. That's pretty scary, because based on that value of Z that we came up with, that measure of the difference between the two averages, we're going to decide to reject H0. In this case, this H0 being that the mean Creighton student was the same height as the mean UNO student, but that's not necessarily the right thing to do. I mean, if I just had a weird sample or something like that, that's not telling us anything about the mean height of the Creighton students. Could very well be an error. I might have rejected the null hypothesis when I shouldn't have, because I just had a stupid sample. I didn't take my sample very well in such a way that it was very representative. But errors can happen the other way around too. Maybe there really is a difference between Creighton students. Let's say Creighton students really are taller than UNO students, okay? But maybe we ended up with some weird sample. Like maybe even though Creighton students are actually usually a little bit taller, we just happen to get a couple of shorter Creighton students, and maybe we just happen to get a couple taller than average UNO students, and in fact we ended up not being able to reject the null hypothesis because the averages turned out pretty close to each other, even though there really is a difference in the height between the Creighton students and the UNO students. That's bad. You might decide you couldn't reject the null hypothesis that they're the same, but they're not the same. Uh-oh, guess what? That's another type of error. Uh-oh. We have ways that this can go right, and there's ways that this can go wrong. In fact, when we designed this experiment with the two hypotheses, there's actually 4 ways the experiment can turn out. Now, this little diagram is going to be hard to understand what exactly is going on here, but I'm going to be making like a little graph here, like a little Venn diagram, if you know that terminology here, just showing that there's 4 possibilities here. The possibilities that are colored in red are going to be situations where H0 really is false. And the possibilities I'm going to color in blue are going to be places where those are outcomes where H0 was actually true. And then I'm going to use this cross-hatching here to show you that there are areas where we actually rejected H0, and there are outcomes where we accepted H0. Or we did not reject H0, strictly speaking. And this divides this little Venn diagram here up into 4 regions. The region that I have highlighted there in black right now is a region where these are outcomes of our experiment, where We rejected H naught, and the truth of the matter is H naught is false. Okay? We correctly rejected H naught. Hooray! We're glad. That is an experiment that worked. For that matter, I'll take you to this little corner of the diagram here, that with blue with the cross hatching from northwest to southeast on there. That is an area where H naught is true, and we didn't reject H naught. Okay, so we ran our experiment, we decided not to reject H naught, and H naught's actually true. Well, hey, that's a good outcome. Our experiment worked. It told us the truth about the world around us. Fantastic. But there's two more areas here on the diagram here. What about this possibility? What if we decided we weren't going to reject H naught? We took our observations, we took our measurements, we said we took our value of Z, which was a measurement of the two averages, and we said, we can't reject H naught. But really, H naught is false. Uh-oh, guess what? That's an error. If we, based on strange samples or something like that, just incorrectly determined we couldn't reject the hypothesis that Creighton students and UNO students were the same height, but they really aren't, that's a problem. That's an error. And in fact, there's another region over here that is up in the top right corner here, where what if we decided to reject H naught? You know, we took our observations and we decided that Creighton students really were taller than UNO students. But what if they're not? What if in the real world, if we actually knew the means, we'd know that the mean Creighton student and the mean UNO student were the same? Uh-oh, that's another type of error. There's 4 ways our experiment can go, but 2 of them are errors. Uh-oh, this is a major problem here. Alright, let's sort this out here. There's 2 different types of errors on here. The one that are up here in the top right corner of the diagram here are what I call a type 1 error. That is when you reject a null hypothesis that's actually true. You're claiming that there's a result here when there really isn't. You're claiming that there's a difference between the height of Creighton students and the height of UNO students when there isn't. You're claiming that the 1990s were warmer than the 1890s when they aren't. That is a type 1 error, to use the right terminology. You possibly have heard this often like on shows or something like that. They'll call that a false positive. We're claiming there's a result, but there isn't. And that will occur with some probability in our experiment when we do our testing of the hypotheses. And in fact, the probability that will happen is given the symbol alpha. Now we'll see that alpha come back many times in the remainder of this lecture. The other type of error that can happen is the one that's in the bottom left corner here, and this is what's called a type 2 error. This is when you don't reject a null hypothesis, but the null hypothesis was actually false. This is when you decided, I can't say that there is a difference between Creighton students and UNO students in terms of height, but there really is. Or you're saying, I can't say based on the data that the 1990s are warmer than the 1890s, but they really were. Okay? When you say you can't claim that the null hypothesis is wrong, but the null hypothesis is wrong, that's a type 2 error. Again, terminology they use in other disciplines or you often see on TV shows or something like that is that's called a false negative. You're saying that there isn't a result, but there really is. Uh-oh. These are 2 different nasty types of errors. Type 2 errors occur with a probability in your experiment too, and that probability is beta. So we have an alpha, which is the probability of a type 1 error, and we have a beta, which is a probability of a type 2 error. We don't want to make errors. We want to manage alpha and beta so that there are low probabilities of making errors. Well, how do these errors happen? That might be useful to know. Alright, type 1 errors happen when we reject a null hypothesis that's actually true. We're claiming that there's a result when there really isn't. Alright, so we computed our value of Z, which is a measure of the difference between the 2 averages, and it was somewhere on the tail of the distribution. And we've wrongly said that that test statistic is far enough into the tail of the distribution for us to reject the null hypothesis. But now, I mean, when you look at the bell curve, it becomes clear that there's a problem. No matter how far you go into the tail of the distribution, there's still probability that even bigger values of Z could happen just by chance, by bad samples and stuff like that. And you don't know if your sample is bad. I mean, if this black arrow here at about 2.4 for a value of Z big enough for you? Or maybe this blue arrow at about 2.7, is that big enough for you? How about this one over here, red one at about 3.2? Well, it turns out, no matter how far you go out into the tail of the distribution, there's always a finite probability that you've not gone far enough and that this result happened just by stupid bad luck in your experiment. You just happened to choose the 10 tallest students at Creighton, just by dumb luck. or you happen to get the 10 shortest students at UNO. It's just dumb luck. Well, guess what? You've made a type 1 error. You've rejected the null hypothesis when you shouldn't have. That's a type 1 error, and it's going to occur with a probability of alpha. Now, it turns out alpha is something you're in control of when you design an experiment. When you design an experiment where you're going to test the hypotheses, alpha is something you decide. You decide, I'm willing to accept, I'll set it to 0.05. That means that there's a 5% chance of making a type 1 error. If that's too high of a probability for you, set it to 0.01 and say that there's a 1% chance of making a type 1 error. And then, based on that value of alpha, you can look up in the back of a stats textbook or the back of a science textbook how big the value of z is going to need to be in order for you to reject the null hypothesis. So, for example, if you set the value of alpha to 5%, that is to say you want to have a 95% confidence in your result, the critical value of z is 1.96. Your value of z will need to be bigger than 1.96 for you to reject the null hypothesis and only have a 5% chance that you are making a type 1 error. We have other values too. You want to make alpha equal to 1%, then there's a value of z, we'll actually see it shortly here, as to, okay, then your value of z is going to have to be bigger than this new threshold. I think it's like 2.97 or something like that. Well, what about those beta? What about the probability of those type 2 errors? Well, type 2 errors happen when we accept a null hypothesis. That is to say, we fail to reject a null hypothesis, but that null hypothesis is actually false. Oh my. For example, let's say we did our experiment, we took our observations, we computed the two averages, we took their difference, we computed z, and we got 1.6. Based on 1.6, I put it on there on the diagram here, is that far enough out in the tail of the distribution that we're going to reject the null hypothesis and say that isn't consistent with what we would observe if the null hypothesis was true? Well, probably not. We're probably going to say we can't reject the null hypothesis, but maybe the null hypothesis is false. Maybe you just had weird, unlikely samples, or maybe you just had the difference between the two means was small. You could come up with a value of z that's not very big, and still it's actually true that the null hypothesis should have been rejected. That occurs with that probability beta, and beta is not something you get to set. Beta is actually a function of alpha and actually the size of the samples that you took. You don't get to set it. Beta comes from these calculations here. And do you get to manage these errors? Is there anything we could do? Can we just say, I'm going to make a alpha really small, so I'm not going to make an error? Or can I do things that make beta small, so I'm not going to make a type 2 error? Well, kind of, yeah. I mean, if I want to reduce the risk of a type 1 error, I'm going to reduce the risk of claiming that I can reject the null hypothesis when I really can't. There's a really simple way to do it. Just keep requiring, set alpha smaller and smaller, so there's a smaller and smaller chance that you are making a type 1 error. That will result in a value of z that has to be farther out the axis. So, like, for example, if you want to use a value of alpha of 5%, if you're willing to accept a 5% risk of making a type 1 error, you only need to have z as big as 1.96. Any value of z that you compute based on your averages that is bigger than 1.96 means that you can reject the null hypothesis with only a 5% chance that you are doing the wrong thing, that you're making a type 1 error. If you feel like having less of a risk of a type 1 error, feel free to set alpha equal to 1%. And if so, then, if I had the number memorized wrong, it's actually 2.57%. 2.57 is your z. Then you are going to need to compute a value of z bigger than 2.57 when you compute your difference between the two means, difference between the two averages, in order to be able to say, I can reject the null hypothesis and there's only a 1% chance that I'm making a type 1 error. Oh, okay. Hey, I can manage these alpha errors. So yes, these type 1 errors, I can manage them. I can determine the level of risk of a type 1 error that I am going to find acceptable. Fantastic! Sounds wonderful. Sounds like I should never have to make an error, except, of course, there's a catch. The problem is there's a trade-off between alpha and beta. See, the farther and farther out on the distribution I'm requiring that my result be in order to reject the null hypothesis makes it more and more likely I'm making a type 2 error, because I've basically made it impossible to reject H0. If I'm saying that I'm only willing to accept a 1% chance of a type 1 error, I've required that z be pretty far out there. Well, very rarely will I get a result that big. Most of the time it's going to be smaller than that, and I'm going to say I can't reject H0. But that doesn't mean that has nothing to do with whether or not H naught is true. It just means you're not rejecting it. So you're not rejecting a null hypothesis that's false. That's a type 2 error. See how there's a trade-off? If I'm going to require that I'm not going to say that my Creighton students and my UNO students are different in height unless the difference is at least 30 centimeters. Oh Lord, 30 centimeters. You're never going to pick a sample that's that big difference. So yeah, you're not going to reject your null hypothesis. I guess, you know what, if you get a sample where the difference is more than 30 centimeters, yeah, well, good for you. You definitely can say that Creighton students are taller than UNO students. And you have a very low probability that you're wrong. On the other hand, what about the times you took a sample and the Creighton students were 10 centimeters taller than the UNO students? Probably that was also the case that Creighton students were taller than UNO students, and you rejected the null hypothesis. You said that they were the same. That's a type 2 error. See, there's this nasty trade-off. Either you accept a risk of a type 1 error, or you accept the risk of a type 2 error, but there's no way around it. This is lousy. In fact, for a given sample size, there's a fixed trade-off between alpha and beta. And the only way around it is to increase the sample size. That's really the only way to make this problem get better. If you took, instead of measuring the heights of 10 Creighton students, you measure the heights of 100 Creighton students and 100 UNO students, your values of alpha and beta can both go down. Now, once they're at the new values, there's still a trade-off. If you make alpha even smaller, beta starts getting bigger. And if you make beta smaller, alpha gets bigger. But the only way out of this trap is to take more observations. And of course, the problem is observations cost money. It costs money to measure these students. And to measure 10 times as much students is going to take more money. If I wanted to have better weather if I wanted to have a better idea of what the mean temperature in Nebraska is right now, a great idea would be to take more observations, but they cost money. There's instruments and people involved and so on. I want to use the smallest sample size I can get away with just for cost reasons. And you can actually see if you take a look at this equation. Again, I told you don't have to memorize the equation, but we're looking at what's going on here. NCU is the number of Creighton students we measured, and NUNO will be the number of UNO students we measured. And you can see that since it's in the denominator here of the square root here, if the value of N and for Creighton and N for UNO increase, these terms are going to get smaller, which means this whole denominator is going to get smaller. Okay, you're going to be dividing by a smaller and smaller number, that's going to get Z bigger. So if we keep taking more, the same size difference between the two averages, but taken using more samples, like having more Creighton students in my sample or more UNO students in my sample, gives us more confidence in our result. So for a given calculated difference, we're going to get bigger values of Z if N is bigger. That's good. That's a way out of this problem. But this trade-off between alpha and beta is one of the nasty problems every kind of scientist works with. And to do a little demonstration of how errors get all over the place, let's talk about a real-world application of a type of experiment we can conduct. We're going to talk about screening for a disease. Let's say that you have developed a new medical test that determines whether or not a person has some rare but serious disease. You're going to take a little blood sample, you're going to do your little experiment. And that experiment has two hypotheses. It can either come up positive or negative. Okay, first of all, it can either come up positive or negative. Either it's going to say you do have the disease, or it's going to say you don't have the disease. And like any kind of experiment, it can go wrong. There is a certain finite probability it's going to give the wrong answer when you run your experiment. So you could think of each time you test somebody's blood as being an experiment, where H naught is that the person does not have the disease. Remember, our null hypothesis, H naught should be the no result, the move along, there's nothing to see here. And our alternative hypothesis, which is exhaustive and mutually exclusive with the first one, should be that the person does have the disease. These are your hypotheses. Alright, there are ways that this could go wrong. Telling a person they have the disease when they don't have the disease is a disaster. If your little experiment that you run comes up with the wrong, decides it can reject the null hypothesis and accept the alternative hypothesis that people have the disease, that is a type 1 error. Alright? You have created a false positive. You have wrongly rejected the null hypothesis that the person is fine. You don't want to do that. Okay? But there is a finite probability it's going to happen. Alpha. That is the risk of that type 1 error. Every time you draw the blood from somebody, there's a fixed chance that you've made a mistake there. On the other hand, telling someone that they don't have the disease when they really do, that's a disaster too. You do not want people going around, you've tested for some rare but serious disease, and you tell them, oh, you're fine, when they actually have it. That's a type 2 error. You have wrongly accepted the null hypothesis. The null hypothesis was that the person was healthy, and you accepted it, but that's not right. That is an example, of course, of a false negative. And it occurs with some finite probability beta. There is some real chance your test is going to give the wrong result. We need to find ways to manage alpha and beta and figure out which of these errors is worse. And because we can't get rid of these errors, we have to manage them. We have to decide which of these kinds of errors is a bigger deal. Which is worse? Telling someone they don't have the disease when they actually do? Or telling someone that they do have the disease when they actually don't? Well, I can tell you that doctors have made that decision. They have decided that the one I've circled there is worse. Telling someone you don't have a disease when you actually do, doctors don't tolerate that. They'd much rather risk the other one, telling you you do have the disease when you don't, and then they'll do another test and then they'll tell you on the second test, oh, it turns out you're fine. Okay? Doctors usually want to make sure that no one with a disease is missed. And so they want there to be a very low chance that's a type 2 error. Okay? Telling someone that they don't have the disease when they really do is a type 2 error. You are incorrectly keeping the null hypothesis. So the doctors are going to tell you that they want to keep beta small. When they're designing a medical test to test if you have some weird syndrome, they are going to want to design the test in such a way that beta needs to be as small as possible. But of course there's a trade-off. If beta is going to be small, alpha has to increase. And that means that we're going to often be telling people they do have the disease when they actually don't. That might come as a surprise to you unless you've had medical tests done. Let me tell you what, if you have much interface with the medical community, you know these things happen all the time, and you get told you have something terrible and then they do a follow-up test and you're fine. But whoops, let's try this here. Let's actually do a little thought experiment. Let's say we have this test, and we're going to test 1 million people for this rare but serious disease. Now, we don't know who has the disease. We don't even know how many people have the disease. But let's say we have a secret knowledge here, like the angels have come down and they whisper the answer to us, okay? And we know that there's actually 100 people out there who have the disease, okay? I mean, in our experiment we don't know, but you and I, okay? That means 999,900 of the people in the million that we screened don't have it. Okay, so if we screen, now those 100 people who are actually sick, when we screened them, there was a 1% chance, because beta is equal to 1%, there was a 1%, 100 times 1% is 1 person. There's going to be one of those people out there, of those 100, we're going to make a type 2 error here. We're going to tell them that they are healthy when they're not. Doctors hate that. Of the 999,900 people who don't have the disease, alpha's 10%. Any given time we run the experiment, there's a 10% chance we're going to tell them they're sick when they're not. 999,900 times 10% is almost 100,000 people. We're going to tell them that they're sick, and they're fine. Think about that for a minute here. Of 100, we're going to tell 100,089 people that they're sick, but only 99 of them actually have the disease, and there's got to be a better way to do it, right? Surely, now don't get me wrong, the rest of those 100,000 people are going to go get second tests and second opinions, and it's going to be fine, but that's why you do go get more tests and you do get second opinions when you're told you're sick with some test or some serious condition, because they're far more likely to be wrong than right. They're willing to accept false positives because they don't want to accept false negatives. Let's see if we can do better. I'll give you a hint, we actually end up doing worse. Let's say if we manage this risk differently, and we're going to set alpha equal to 1%, but that pushed beta up to 10%. Okay, let's do our little thought process here. We're going to test 1 million people, and of the 100 people who actually have the disease, there's a 10% chance of a type 2 error, so 100 times 10% is 10 people. Of the 100 people out there who actually have the disease, I don't know which ones they are, until I test them and I find 90 of them, I find them, and I say, you are sick, go get the treatment. But 10 of them are people I told were healthy, and I don't know which 10 they are. Oh, that makes the doctor very unhappy. They don't want that. And of the 999,900 people who really are sick, who really are healthy, 999,000, we have a 1% chance of making a type 1 error, so roughly 10,000 people are going to be told they're sick when they're fine. Uh-oh, that's type 1 errors. So we're going to tell a little over 10,000 people that they're sick. We're going to tell them that they tested positive for our rare but serious medical condition. But only 90 of those people are actually sick. Okay? And that's still an awful high false positive rate. And 10 sick people are still out there not getting treated. Doctors hate that. They'd much rather give you more false positives and have fewer people getting away with a false negative. Oh man. Errors suck. Oh man, scientists just hate this. They hate the fact they can design a hypothesis, they can research a question, they can go all through the scientific method, and there's still this risk they have to manage, that they're just making mistakes because of experimental design and experimental random samples of errors and so on. Errors are why we don't talk about these kinds of experiments as proof. Rather, they have certain confidence levels or certain statistical significance. If we say that results are significant at the 95% level, what that means is there's only a 5% chance that we have incorrectly rejected the null hypothesis, that there's nothing going on. But that sucks. It really hurts that we have to, put caveats on our research, and we could be, no matter how good your results are, you always have risks that you're making errors. We say that the result is statistically significant, or that we have a 95% confidence level. What that means is we have managed the risk of type 1 errors such that we have only had a 5% chance of making an error. Now in the climate sciences, we don't accept risks even that high, especially not on the subject of global warming and so on. We are going to be designing our experiments in such a way that we have managed the risks and make sure we're not telling people things that aren't true. And you'll see why and how in the questions that I'm going to be asking you. Alright, so question 5. The value of alpha determines the probability of making a blank error, which is also known as a blank. Type 1 or type 2, and false positive or false negative. Which one is what is managed by the probability alpha? Alright, make a choice from these 4 options and get a little feedback before you move on to question 6.